In example 6, we're asked to compute the Laplace transform of f of t equals cos of t. Well, actually, a little more generally, cosine of some coefficient times t. And I'm going to use a little trick here. I could go ahead and just plug this function into the definition and then grind through the details. I know that that would require me to do one of those integrals that's integration by parts in a sort of feedback loop. So I could track down an appropriate formula as I did for cosine just a few examples ago. But what I'd like to do instead, sort of as a shortcut, is I'd actually like to define, say, g of t to be sine of a t. Then notice that if I take the derivative of that g, I would get a cosine of a t. So I can calculate the Laplace transform of cosine in terms of the Laplace transform of sine. Let me show you how this will work. First, let me write cosine of a t as g prime of t over a. And then if I'm interested in taking the transform of cosine of a t, I can instead take the transform of g prime of t over a. Let me first plug that into my definition, which gives me this integral here. And then you notice, again, this integral is an integral with respect to t. So this a is a constant, so I could certainly move that a outside the integral. And then this integral is recognizable as the transform of g prime of t. But we know what the transform of g prime of t would be based on example 4. So let me write that out. Now in example 4, I had done the calculation or the computation of the Laplace transform, assuming that I did not know what g was, or in the case of example 4, the function was labeled f there. But here, I know exactly what little g is, and I know what capital G is. Little g is this function here, sine of a t. Plugging t equals 0 into this original little g of t gives me sine of 0, so that simplifies to just 0. And then capital G of s needs to be the Laplace transform of little g of t. We actually calculated the transform of sine a few examples ago, so I can go back in and make that substitution. So here I've substituted in what I know to be the Laplace transform of sine of a t. Now I can do a little bit of simplification. These a's will cancel. This s will end up in my numerator, and I can write that the transform of cosine of at will be s over s squared plus a squared. So once again, this is a general formula that I can apply to any cosine. So if I have cosine of 6t in a particular problem, then I can straight away identify that its transform will be s over s squared plus 6 squared. Theorem 2, which shows up next here, gives us a couple properties that are true in a pretty intuitive way. In fact, let's take a look. In Theorem 2, it says if we have two Laplace transforms, if we have two functions, f of t and g of t, and we know that their Laplace transforms exist, and in addition, if I've got some scalar c, then first of all, the Laplace transform of a scalar times a function is simply the scalar times the Laplace transform of that function. We actually utilized that step in example 6 here, where I said, since my Laplace transform is defined as an integral, I'm accustomed to identifying a scalar and moving it outside the integral. That's essentially the justification for property A. Property B is also intuitively true if we remember that this Laplace transform operator is an integral. And so if you think of this generally as saying the integral of f plus g, then you know that we can break that into two separate integrals, the integral of f plus the integral of g. If I use the two conclusions from Theorem 2 together, this tells me I can take the Laplace transform of any linear combination of functions, and I can break that down into individual Laplace transforms that are then combined appropriately. We demonstrate that in example 7. Here in example 7, I'm asked to take the Laplace transform of an expression containing three separate functions that have been added together with different coefficients. Now, on the one hand, I kind of should drop this straight into my definition, but instead I'm going to apply Theorem 2, which indicates, first of all, that the Laplace transform of a sum of functions is the sum of the individual Laplace transforms. In addition, I know that these coefficients, for example 5 here in front of t squared, will be able to move outside the integral, move outside the Laplace transform. So I think I can rewrite this as this sum of coefficients times Laplace transforms of individual functions. Now, once again, I could implement the definition and identify exactly what the transform of t squared would be, but that's work that we've already done. In fact, we have a theorem which now tells us that t to any integer power, we know how to calculate its transform. So when we have such theorems, we will not rely on the definition. We'll simply go straight to those theorems. Notice the same is true for sine of 4t, and the same is true for e to the 2t. So I don't think I will have any integrals to evaluate in this problem. So utilizing results that we've developed so far in this section, I can state the necessary transforms straight away. This is really our ultimate goal. I want to rely on the definition in terms of the integral as rarely as possible. So as I mentioned at the beginning of this section, our goal is to build up familiarity and sort of a catalog of transforms of known functions so that when I encounter something like sine of 4t, I know straight away that its transform is 4 over s squared plus 4 squared, and I don't have to rely on using the integral definition. All right, we have just a couple more things to work through in this section. The next little paragraph here actually references Theorem 2. In Theorem 2, for example, in Part B, we said that the Laplace transform of a sum is the sum of the Laplace transforms. So this paragraph asks, is the same thing true for a product? And hopefully you recall that when dealing with integrals generally, we are not allowed to integrate a product by simply integrating each individual factor and then multiplying. This does not work. So if I look for the transform of f times g, it is generally not true that I can simply take the transform of f and then multiply by the transform of g. I would like this to be true because it would be very convenient, but it is not in fact true. That said, we have Theorem 3, which indicates a specific product. Let's take a look. In Theorem 3, I'm not multiplying two arbitrary functions. I have one arbitrary function f of t, but then the other function in my product is a specific function, namely e to the ct. And this theorem tells me how to evaluate the Laplace transform of this type of product. I'll just reiterate before we look at the proof that this doesn't work for just two arbitrary functions, f of t and g of t. This only works when I have the function e, an exponential, multiplied by some other function. The proof of this theorem will be an application of the definition. So let me go ahead and multiply this, let me substitute this expression into the integral definition for the Laplace transform. Now, in this integrand, I have three factors multiplied. Two of them are similar because they're both exponentials, so I'll group those together. And here I've actually written them as a single exponential. Since they have the same base, when I multiply those exponentials, I will add their exponents. And then, as we've seen previously, I can factor the t out of this exponent. And then one additional step. In my original Laplace transform definition, I always have e to the negative s to e to the negative something t. So when I factor the t out, I'm going to factor a negative out of the front as well. Here, let me show you what I mean. So here I've factored the t out, but then I've also factored this negative out. I would take a second to just confirm if you multiply all of this, you do in fact get this exponent here. So now this looks like the definition of a Laplace transform. It looks like the transform of f of t. But instead of just having s in the exponent, I now have this sort of more complicated quantity s minus c. So the way that we conclude is by saying that this integral is in fact the transform of f, which I would typically write as the Laplace transform of little f. But instead of this Laplace transform, which is normally in terms of s, I have the quantity s minus c plugged in. So one way to indicate that is to say that this transform is evaluated at s minus c. Alternatively, this other notation we could say we're going to get the transform of little f, which would be capital F, but instead of that being a function of just s itself, it's now a function of this more complicated quantity s minus c. As you'll see in the next example, practically speaking, what I do when I encounter an exponential times some other function is I find the transform of that other function, f here, and then whatever coefficient on t exists in the exponent, I'm just going to shift my s variable by that. So this is sometimes referred to as a shifting theorem because in the transform we have shifted by c. So let's put all this together and take a look at one last example. In example 8, we're given a differential equation. This is a pretty familiar looking differential equation in that the left-hand side is linear, has constant coefficients, second order. So this is exactly the type of differential equation we would have encountered in chapter 3. The right-hand side is a little complicated. So if I had to use undetermined coefficients or variation of parameters, I would expect I'd have a lot of calculations to do. Notice again, in this example, we're not asked to solve this differential equation. We're simply asked to compute the Laplace transform of the entire differential equation. Basically, I'm going to apply the Laplace transform operator to this entire equation. Using Theorem 2 above, I know that I can take the transform of the individual components. I can factor out coefficients whenever necessary. So there will be quite a few Laplace transforms to evaluate, but I believe I'll be able to calculate them pretty efficiently based on the work we've done so far in this section. So let's give it a shot. So here I've started applying the Laplace transform to the individual terms. This is what will happen if I take the Laplace transform of the left-hand side. I'll have all of these individual Laplace transforms. Let me continue doing that same thing on the right-hand side. So I do, in fact, have a lot of Laplace transforms to compute. Some of these are going to be easier than others. Let me start with some of the easy ones. If I look at this last one out here, I have 3 times the transform of sine of t. Transform of sine of t we can now evaluate directly based on the results we've developed in this section. So I'll be able to write that that transform is equal to 3 times 1 over s squared plus 1. Working my way to the left, if I look at this next one, I've got e to the negative 3t cosine of 4t. This is e to the t times some other function. So I could think of the cos of 4t as like an f of t, and then this is set up with exactly the structure required by the previous theorem. I've got e to the something times some other function. So I can apply that theorem, and I will find the transform of cos of 4t. But instead of plugging s in as the independent variable in that transform, I will plug in s minus negative 3, or s plus 3. So I think this is what I get. So if I was asked for the transform of cosine of 4t, that would be s over s squared plus 4 squared, or 16. Based on Theorem 3, since this cos of 4t is multiplied by this exponential, instead of just having s as the independent variable, I've made this substitution of s plus 3 in instead. And of course this negative 2 is sort of along for the ride as a coefficient. Working my way to the left, once again, could think of this as like a function times an exponential. So I could once again apply Theorem 3. So based on a previous result, the transform of t to the first power is 1 factorial over s squared. Since that input function t is multiplied by the exponential e to the negative t, instead of that transform being in terms of s, it will be in terms of s plus 1. All right, that was the right-hand side. That wasn't too bad. Now, on the left-hand side, I have an unknown function y. I don't know what y is. Therefore, I can't know what its transform is definitively. So what I will do instead is either leave this transform in this notation here. Simply say the transform of y is the transform of y. Or, to clean things up a little bit notationally, what I'll do is I'll write this transform of y as simply capital Y. So the capital Y that I have written here is the transform of the unknown function y. Working my way backwards, we had a theorem earlier for f prime of t, and that was in terms of the transform capital F. And so I can apply that theorem here, and my transform will be in terms of the variable capital Y. So applying that theorem, I get these two terms here. Again, I don't know what capital Y is, but I know that it's the transform of this unknown function, little y. And so when I take the transform of y prime, I get s times that transform minus little y of 0. And then we also have a theorem for the second derivative. Let me plug that theorem's result in. So I think when all is said and done, this is the transform of the original differential equation. For this particular problem, we were simply asked to compute this transform, so we don't have to push it any further or do any additional steps. But I would like to clean it up a little bit algebraically and make a couple more comments. First of all, I will remind you that these terms, y of 0, little y prime of 0, little y of 0, these are just constants. These are initial conditions, and so those are some constants which, in the context of a real differential equation problem, are probably provided to me. The second thing that I'd point out is that then the left-hand side has a few of these capital Y terms. And those capital Y's are the transform of an unknown function. Actually, those capital Y's are the transform of the solution of this differential equation. Let me do some algebra. Let me move these constant terms, or these terms with initial conditions, over to the right-hand side, and then let me do a little factoring to clean up this capital Y. Here's what I get. So here I have kept the capital Y terms on the left and then factored the capital Y out. And then I moved these initial condition terms over here to the right. First, let me point out that this quadratic s squared plus s minus 6 is exactly the same as the characteristic polynomial of the homogeneous version of our differential equation. And that is no coincidence. That should always happen in this type of problem. And then the last thing I'll do is let me actually divide by this quadratic. Okay, so I admit that this expression is a little crazy, a little complicated, but let me just kind of give the general sense of what's going on here. I have divided through by this quadratic, and then I have all these terms here. So essentially, all of the terms on the right-hand side could be considered the Laplace transform of some function. I certainly recognize these as being Laplace transforms of a function because I just calculated them as Laplace transforms. Since I have this s squared plus s minus 6 multiplied through by everything, it's not quite as simple as that, but generally speaking, I would say that this right-hand side is a sum of the Laplace transforms of a bunch of functions. This left-hand side is simply capital Y, the transform of the unknown function, which is the solution to my differential equation. So we won't work through the steps here, but you can imagine that if I could untransform this equation, on the left-hand side, capital Y would be untransformed to lowercase y. And then if I went through and carefully untransformed all of the components on the right-hand side, then I would identify the solution of this differential equation. And that's exactly our goal. We're not quite ready to do that yet, and this example is actually pretty complicated, but I did want to kind of talk through those details as an introduction to what our ultimate goal will be, and just to preview what we'll be doing over these next couple sections. So in this section, we've worked through quite a few examples, and hopefully you've gained quite a bit of familiarity with this operator, and you're starting to get a sense of the transform of some known functions.